Hi everyone, this is Kunzo. It's my pleasure to introduce our work exploring motion, ambiguity, and alignment for high-quality video frame interpolation. Let me begin by providing a brief overview of our approach. In this paper, we present a high-quality method for video frame interpolation and extrapolation, termed VFI and VFE. It has two main components. First one, we introduce a novel TCL supervision technique to address motion ambiguity problems. Secondly, we developed an effective GCSPA to accumulate cross-scale information and utilize the field's feature as guidance to improve alignment accuracy. Thanks to these innovative designs, our model achieves state-of-the-art performance in both VFI and VFE. As shown in the figures, our method produces better visual results than SOTA models. Furthermore, the figure on the right side suggests that TCL can enhance previous VFI models. Let me begin by providing a brief overview of our approach. In this paper, we present a high-quality method for video frame interpolation and extrapolation, termed VFI and VFE. It consists of two main components. First, we introduce a novel TCL supervision techniques to address motion ambiguity issues. Secondly, we developed an effective GCSPA to accumulate cross-scale information and utilize the field's cross-scale feature as guidance to improve alignment accuracy. Thanks to these innovative designs, our model achieves state-of-the-art performance in both VFI and VFE. As shown in the figures, our method produces better visual results than state-of-the-art models. Furthermore, the figure on the right side suggests that TCL can enhance previous VFI models. As mentioned before, there can be multiple solutions that perfectly explain the input frames. However, existing VFI method relies on a one-to-one MSE and MAE losses for strict supervision, which penalizes the model if its predictions do not match the predefined ground truth exactly. This can lead to the model producing an average result of those possible solutions, resulting in blurry image contents. To address this issue, we propose a texture consistency loss for auxiliary supervision, which aims to relax the one-to-one constraint of the MAE and MSE losses. Furthermore, we have developed a guided cross-scale parameter alignment method that accumulates cross-scale information to achieve more accurate temporal aggregation and produce high-quality interpolated results. As demonstrated in the visual examples below, our method generates clear details compared to SOTA methods. The proposed VFI architecture is illustrated in this figure. Firstly, we extract multi-scale image features from two input frames. Then we perform the guided cross-scale parameter alignment to obtain two fused features. Later on, we utilize an attention-based fusion module to aggregate the two aligned features. Last, the reconstruction module outputs an intermediate frame by taking the aggregated feature as input. As can be seen in the equation, TCL relaxes the rigid one-to-one constraint, allowing more flexible supervision as long as the prediction contains consistent content with input frames. Given a predicted image patch, TCL searches for the location of the most similar patch from two input frames with the lowest L2 distance in the synthesis transformation space. Once we have found the optimal 2D position of the matched patch, we extract the RGB patch for additional supervision. We have observed that existing parameter alignments may not effectively explore cross-scale fusion for large motions. In this work, we introduce a guided cross-scale parameter alignment approaches, which employs fused cross-scale alignment features as guidance to improve multi-scale alignments. Additionally, we accumulate all previously aligned information for better reconstruction outcomes. Like most VFI and VFE methods, we train our models on Waymo-Chevrolet chain and evaluate them on three popular benchmarks, and we adopt PSI and SSIM for objective assessment. Following most VFI and VFE models, we train our models on Waymo-Chevrolet chain and evaluate them on three commonly used testing benchmarks. Our primary evaluation metrics are PSI and SSIM. Then, we examine the detailed configuration of our TCL. As indicated in the first two tables, appropriate hyperparameters lead to better performance, and in the third table we observed that patch matching in the CT space is more effective than the RGB space. The table presents a quantitative comparison with SOTA methods. It is evident that our two models achieve the best and second best result in most cases. Here are some visual examples. It is clear that our approach recovers fine details, more comparing patterns, and sharper structures when compared to SOTA VFI models. When it comes to extrapolating future frames, it is more challenging than VFI task. Nevertheless, our approach consistently outperforms all other VFE methods as validated by the table. Furthermore, our proposed TCL supervision can improve previous SOTA methods even further. The visual comparison also confirms the advanced performance of our VFI model. This image demonstrates that our method can generate best extrapolation results. This image showcases that applying our TCL to subcon can produce visually pleasing results compared to its counterpart trained with conventional one-to-one loss. It is also observed that TCL improves the compatibility of SOTA VFE models. Thanks for your listening.